6:45 p.m., the evening of July 16th. At Starbase, Texas, the 33 Raptor engines on the Super Heavy ignited in unison. But in under a second, every single engine went completely dead. Water from the deluge system had just come down. The 33 Raptor engines fired for less than a second, then all cut out together. This is something the SpaceX team itself termed an anomaly. A day later, Elon Musk spoke, not to explain the whole thing, only to confirm one fact. 2 Raptor engines would be removed. The question at hand is not what happened. It is this: why did just 2 out of 33 engines end up deciding the fate of the entire flight? To answer that question correctly, I need to take you back to another event. An event that took place just 3 days before Flight 13 was set to lift off. 3 days. That is the gap between the moment the U.S. Federal Aviation Administration, the FAA, officially closed its investigation file and the moment Flight 13 stood on the launch pad. 3 days before 33 Raptor engines shut down together, the FAA had just released its findings on a separate incident, one that occurred on this very same engine line, only 2 months earlier. Very few news reports set these two events side by side. But here's the critical detail. The incident on July 16th was not the first time a Raptor engine on Super Heavy had run into trouble at startup. It was the second time in under 2 months. Let me take you back to Flight 12 on May 22nd, so you understand the full context. On that flight, after Starship separated from the booster stage, the Super Heavy booster performed a maneuver called the flip, reorienting itself to prepare for the return flight to the landing site. This is one of the most complex phases of the entire flight, because the booster must maneuver with precision while still traveling at enormous speed. At that exact moment, 5 of the 33 engines failed to relight as planned. Picture it this way. If you are driving a truck with many wheels, and 5 of those wheels suddenly lose their brakes at the same time, the truck can still stop, but no longer along the trajectory you intended. That is exactly what happened to Super Heavy. The boost back burn, the burn that sends the booster flying back toward the landing site, ended earlier than planned. The booster lost the ability to control itself for a controlled landing in the Gulf of Mexico. The incident was severe enough that the FAA was compelled to open a formal investigation in accordance with the mandatory procedure that applies to every commercial launch in the United States whenever an unplanned incident occurs. For the entire duration of the investigation, SpaceX was barred from flying any further Starship missions. That investigation closed only on July 13th, exactly 3 days before Flight 13. According to the official findings, fully documented by the in-depth technology outlet The Register, there were 2 root causes behind the Flight 12 incident. The first cause, thermal effects acting on propulsion system components while the rocket was ascending. The second cause, a configuration error in the engine warning system, which caused the system to misread its signals. In other words, the engine may in fact have been functioning normally, but the monitoring system misread this as a fault and intervened automatically. If Flight 13 had been the first time a Raptor engine ran into trouble, you could quite reasonably treat it as a random, isolated incident. Nothing to be concerned about in the long term. But set alongside Flight 12, where 5 engines likewise ran into trouble on restart on this very same Raptor line, the picture looks entirely different. What the data suggests is this. These may not be 2 wholly separate incidents at all. They could well be 2 different manifestations of one and the same underlying set of problems, the reliability of the Raptor engine when it must start or restart under conditions of extreme pressure and temperature. And this is precisely the connection that an analytical engineer needs to examine first, before rushing to any conclusion. Inside 33 lighters. Before going further, I want to explain briefly why igniting so many engines at once is so difficult in the first place. Because this is precisely the root of both incidents, Flight 12 as much as Flight 13. Imagine trying to strike 33 lighters at the exact same instant. Each one needs the correct amount of gas, the correct pressure, the correct spark, all within an almost identical moment. If just one of them is off by a few thousandths of a second, the entire system can fall out of balance. That is exactly what has been unfolding inside Super Heavy. Not on one occasion only, but across both of the 2 most recent flights. The difference lies here. In Flight 12, that lighter had to relight in midair. after having already been put through the extreme heat of the initial ascent. In Flight 13, that lighter had not even managed to light for the first time, while still on the ground. This is a meaningful distinction, and it is what gives rise to two possible scenarios for what happens over the coming week. One point that deserves acknowledgement: SpaceX did not simply sit idle after Flight 12. According to the in-depth Starship-focused outlet NASA's Spaceflight, the Booster 20 stage, the very booster whose flight was just scrubbed in this incident, had been physically modified relative to previous boosters. The forward dome of the booster was reinforced with an additional layer of heat-resistant shielding to withstand a technical phase known as hot staging, the moment when the upper stage ignites its engines while still attached to the lower stage, rather than separating fully beforehand. This is one of the most thermally extreme phases of the entire flight, since the exhaust plume from the upper stage engines is blasted directly down onto the very top of the booster. More notable still, SpaceX added a reinforcement plate at the exact location where an earlier booster, Booster 18.3, had once been dented during a pressure test, informally known as a can crush test, carried out back in January of this year. In other words, SpaceX knew precisely where the structural weak point lay and had proactively reinforced it before this flight. This deserves to be acknowledged fairly. It is not the picture of a company disregarding the lessons of the previous flight, rushing to fly again merely to stay on schedule. It is the picture of a team that read the investigation report closely, identified the correct weak point, and acted before being forced to. But this is also exactly where the story becomes more worth dwelling on. If the weak point that caused the Flight 12 incident had been reinforced this thoroughly, then why did the engines still run into trouble at startup on Flight 13? Based on all the data currently available, there are two possible scenarios, and each one leads to an entirely different outcome for the schedule ahead. Scenario 1. Two independent problems, unrelated to one another. Flight 12 experienced a failure restarting engines mid-flight in a near-vacuum environment, after the engines had already been put through the extreme heat of the initial ascent phase. Flight 13 experienced a failure at the very first startup itself, on the ground, under ordinary atmospheric conditions, without having gone through any thermal stress beforehand. Technically speaking, these are two entirely different operating scenarios. If that is indeed the case, then this is most likely nothing more than an isolated, localized fault specific to Flight 13, perhaps an assembly error, a sensor fault, or some minor detail bearing no relation whatsoever to the cause of Flight 12. In this case, the early next week timeline Musk gave is entirely feasible. Scenario 2. The same root cause, simply manifesting at two different stages. If the true cause does not lie in the booster structure, the very thing SpaceX just reinforced, but instead lies deeper in the design or manufacturing process of the new generation Raptor engine itself, then reinforcing the booster's outer shell will not solve the underlying problem, simply because the shell was never the real cause. In this case, the early next week timeline will most likely keep slipping, not because SpaceX lacks resolve, but because the nature of the problem demands a far deeper investigation than merely replacing two individual engines. There is one very concrete signal you can use to tell these two scenarios apart, once SpaceX's next technical report is released. Watch for whether that report repeats the exact same phrases that appeared in the Flight 12 investigation findings, specifically thermal effects on the propulsion system, or engine warning system. If those phrases resurface, that is a clear sign the two incidents share a common root cause. What the market already knew before you even read the news. There is one detail few people noticed, yet it reveals just how much real tension surrounded this flight, even before the engines shut down. According to CNN, on the very day of the launch, SpaceX's stock had already fallen below its IPO offering price, following a none too favorable trading session beforehand. And after the scrub, the stock fell by a further 3+% in after-hours trading. This marks the first time in the history of the Starship program that a launch scrub was not simply technical news for rocket enthusiasts. It is financial news, one the market reacted to almost instantaneously, in real time. This places SpaceX in a situation without precedent across the entire development history of Starship. The test fast, fix fast culture, once regarded as normal, even praised within the commercial spaceflight industry, is now unfolding under the watchful eyes of thousands of investors, each reacting financially to every single delay in their own way. If you are wondering why Musk's statement this time was shorter than usual, just a single sentence, without the lengthy explanations of previous occasions, this may be part of the answer. Every public word now carries the potential to directly move the stock price, not merely to stir the feelings of the rocket fan community. This is an angle very few Starship analysis videos touch on, because most channels focus purely on the technical dimension, overlooking the fact that this program is now operating under two parallel pressures at once: technical pressure and capital market pressure. If you want to know the moment that technical report is published, and I will read through it line by line to break it down for you, exactly as I have just done with the Flight 12 report, hit subscribe right now. Why 20 minutes from 20 satellites still matter, even though the flight has not yet managed to lift off? There is one thing you need to know in order to understand why SpaceX is willing to wait rather than rush to fly again as soon as possible. This flight is not simply an engine test. It marks the first time Starship has carried 20 next-generation Starlink satellites, version 3, satellites that are genuinely operational, not mass simulator models like those on the 6 previous test flights. These satellites are anything but trivial from a technological standpoint. Each one is capable of transmitting data down to the ground 10 times faster than the current generation and uploading data 22 times faster. If the current generation of Starlink satellites is like an ordinary household water pipe, then this new generation satellite is like a large diameter fire hose. The same span of time, but a vastly greater volume of data flowing through it. 6 of these 20 satellites are additionally fitted with a special camera set, tasked with scanning Starship's own heat shield and transmitting that footage back to the engineering team within the brief 20 minutes before re-entry into the atmosphere. In other words, these satellites are not merely cargo. They also function as a miniature film crew, documenting the very health of the ship carrying them. And this is precisely the real reason SpaceX is willing to accept a delay rather than rush back to flight. If the vehicle were to launch, but the engines ran into further trouble at a later stage, during ascent, say, or during stage separation, then the one and only opportunity for these 20 satellites to demonstrate the new connectivity mechanism would be lost entirely. In other words, the cost of a delay of a few days is far smaller than the cost of losing all the data from this very first batch of next-generation satellites. Flight 12 was once expected to be the perfect stepping stone toward the V3 generation. It was not perfect, but it was good enough to keep flying. Flight 13 was expected to fix everything Flight 12 left behind. It did not get past the very first second. Now, what stands between Starship V3 and this generation's first successful liftoff is no longer a question of rocket technology. It is the question of whether SpaceX is fixing the right problem or only fixing what it can see.